the above video, we know that m can be split into m1 and m2. Here m1, m2, we split the norm means less than or equal to norm of x plus m1 plus norm of y plus m2. m1, m2 belongs to capital M. That is equal to infimum. If we substitute infimum means infimum of this term and infimum of this term, which is known as norm of x plus m plus norm of y plus m. So n by m is a norm linear space. Then we have to all the conditions of x plus m satisfies the norm definition, so it is a n by m is a norm linear space. So next what we have to prove means, if to prove n by m is complete when n is given to be complete, n complete means n by m is complete. For that complete, there we have to prove, instead of complete we have to prove, that is equivalent to prove Cauchy sequence in n by m is convergent in n by m. We have to take the Cauchy sequence in n by m and we have to say that that is convergent in n by m. Also we have to know that Cauchy sequence is convergent if and only if convergent subsequence exists. So Cauchy sequence is convergent means there exists a convergent subsequence. So we have to obtain the subsequences. So xn plus m of a Cauchy subsequence. So for the subsequence there exists means norm of xn plus m plus x minus x m plus 1 xn plus 1 plus m, that is less than or equal to 1 by 2 power n. This is the sequence, Cauchy sequence, which is xn is convergent for given epsilon greater than 0 for all m comma n greater than or equal to n naught, which is norm of xm minus xn less than epsilon. Here we take the epsilon as 1 by 2 power n. Now we have to prove that the subsequence is convergent in n by m. Okay, so if we prove convergent, which means subsequence is convergent means it is a Cauchy sequence is a convergent. Okay, now we choose the vector y1 as, now we have to prove that this subsequence of the Cauchy sequence is convergent in n by m. Now we choose any vector y in x1 plus m. So y1 in x1 plus m, the element is y1 equal to x1 plus m. It is, we choose y1 in this set and the element is y1 equal to x1 plus m, m1 x1 plus m1. Here m1 belongs to capital M. Since norm of x1 plus m minus x2 plus m less than or equal to 1 by 2, so we take the infimum. So infimum is, it can be written as norm of x1 plus x2 plus m, so it is less than or equal to 1 by 2. The norm condition is, we from the given question we know that infimum of norm of x1 minus x2 plus m belongs to capital M. For all m naught belongs to capital M, we choose m naught belongs to capital M, norm of x1 minus x2 plus m naught less than 1 by 2. So here norm of x1 plus m1, we add and subtract plus and minus m1. So x1 plus m1 minus x2 plus m minus m naught plus m1 less than 1 by 2. Okay, then what we know that this is y1 minus y2 less than 1 by 2, y2 equal to x2 minus m naught plus m1. Here x2 belongs to this values or belongs to x2 plus m. This is known as, this also belongs to the m. So y1 belongs to x1 plus m. We have obtained that y2 belongs to x2 plus m such that norm of y1 minus y2, that is also less than 1 by 2. Okay, then for 1 and 2 we have that terms. For we have to find all the subsequences. So y3 is this one, so we get y2 minus y3, because here is y1 minus y2 is less than 1 by 2. Then and next subsequence is y2 minus y3 less than 1 by 2 power 2. For all general terms we can get y1 minus yn plus 1 less than 1 by 2 power n. Whatever the first value is 2 power n. So we will prove that the sequence yn is Cauchy sequence in n. For given epsilon greater than 0, there exists a finite integer. That integer is 1 by 2 power n naught minus 1 less than epsilon. So now for m less than n, we choose both m and n naught, or this is the Cauchy sequence condition. For given epsilon greater than 0, there exists an integer and m less than n for both m comma n greater than or equal to 0. We have general term of yn minus yn, which is y, if we define means ym minus ym plus 1 plus we have divide the sequence into subsequences: ym plus ym minus ym plus 1, ym plus 1 minus ym plus 2, yn minus 1 minus yn. Taking the norm means less than or equal to, this can be written as 1 by, because yn minus yn plus 1 can be written as 1 by 2 power n. So ym plus 1 can be written by 1 by 2 power m plus 1 by 2 power m plus 1 by 2 power n minus 1. This is the sum of the finite geometric progression. The finite geometric progression is less than infinite geometric progression. So geometric progression is a divided by 1 minus r. A is the first value, 1 by 2 power m, 1 by r is the difference between two values, 1 minus 1 by 2. So 1 by this is 1 by 2 power m, this is 2 by 1. So 1 by 2 power, this is 2 goes to this side. If we take means 2m minus 1. Okay, then for m minus 1, we compare this n and we compare this m and n. Okay, 2 power m minus 1, which is m greater than or equal to n naught. See here, m greater than or equal to n naught. So minus 1 means it also minus 1. 2 power means also greater than, but if we take the reciprocal means less than. So it is in the form of reciprocal, it is less than 2 power n naught minus 1, it is less than epsilon. So it is also convergence to some epsilon. So yn in the Cauchy sequence in n, but n is a complete. We know that n is complete. By definition, complete means it definitely converges. So yn converges to y for some y belongs to n. What we have to prove means that sequence, what we have to prove in case of the quotient spaces, xn plus m converges to y plus m in that space. Okay, for that what we do means xn plus m minus x plus y equal to